This transformation is called a reflection. And a reflection is when we either change the inputs, the x coordinates, or the outputs, the y coordinates, by changing the sign, i.e. from a plus to a minus or a minus to a plus. Let's see what it looks like. We're going to look at vertical reflections first. So here we have our usual table of values represented by these points here on the graph. And we're not going to touch the x coordinates. That's going from -5 to 5. We're just going to say whatever happens to the function, whatever it outputs, I'm going to make the result negative. So f of -5 is -5 squared, which is 25. And so now it becomes -25. I'll keep on doing the other ones. You trace what it does by looking at the graph. Okay, here we've got 0 is equal to 0 squared. So f of 0 is 0, and -0 is just 0 as well. So it doesn't change. Look at that. It stays there. Now, what makes a quadratic function, or at least the base function, maybe not unusual, but particular, is that originally all of the function values were positive. Okay, doesn't matter whether you put a negative number in or a positive number, when you square it, the output is positive. So all of the function's values are positive. So it kind of makes sense that when I then make every single one of those outputs negative, we're getting this kind of shape, exactly the same shape as above, but it's underneath the x-axis instead of on top of. Now, think about this like what we're seeing here is a mirror image of what's happening here. So if you can imagine there's a mirror put here on the x-axis, then what you're seeing here is reflected down here, which is why we call this transformation a reflection. It's reflecting about the x-axis. So reflecting about, and then what is it? Is it reflecting over? The x-axis. So we say reflecting about the x-axis, like so. Okay, where it hits the mirror surface, which is 0, 0, it hasn't changed at all. Okay, but what used to be -5 squared equals 25 is now -5 squared is 25, but make the coordinate negative, so it's now -25, and so on. Okay, so that's how that works. So to represent that as a new function, we would say the new function is y equals negative f of x. Okay, so all the x hasn't been touched, but the outputs have been. And there we go. It's tracing through those points as you'd expect. F of x, of course, the base function is x squared. So f of x can be replaced with x squared because they are the same thing. And so we can simply write the function as y equals negative x squared. As I turn that on, you'll see that it perfectly covers the y equals negative f of x graph. Okay, so that's what the function looks like. If you had y equals negative x squared, then you would expect to have what we call a concave down graph. Concave down. Imagine this is like a cave opening and it's facing downways. This is concave up. Okay, what about a reflection about the y-axis, a horizontal reflection? Well, it goes a bit weird, to be honest. Not weird, but you'll see. So I'll turn those dots off and I'll turn these dots on. And what I have here is I've color coded them for a reason, but effectively I've got the same range of numbers. I've got -5 to 5, and I've got f of -5 to f of 5. So these match up. But this time I'm going to keep the y coordinates the same, and I'm going to convert these to negative. Let's see what happens. So -5 becomes -5, and we know what that is, don't we? Minus minus is just a positive. -4, -4, -3, -2, -1. -0 is just minus. 1 becomes -1. 2 becomes -2. 3 becomes -3. Can you see what's happening? The purple dots were over here and the orange dots were over here. And now as I'm going through, the purple dots are appearing on this side and the orange dots are moving from there to there. -4. There we go. The point's gone from there to there. -5. The point is going from there to there. But it looks the same, right? It looks the same. So the reason why is because if you reflect about the y-axis, like so, if you reflect about this axis here, because our graph is symmetrical, which means that the left-hand side is the same as the right-hand side through the middle of it, when we flip the graph, it actually looks exactly the same. So although it looks, so you can see the points of flipped location, but for all intents and purposes, it is exactly the same graph. So it's kind of not that interesting in a way. So looking at that again, we've got y equals f of minus x. So if I press the minus there, you'll see it's now got a red graph going all the way through here. Now f of minus x is the same as putting in a minus x here. I have to put it in brackets because that means square x and make it negative. I have to put the negative x in brackets to say I'm squaring negative x. So the rule becomes negative x squared, and of course the graph is now perfectly aligned along here. Okay. I wanted to show you something really quickly though. So far we've been transforming the base graph f of x equals x squared, but you can transform any function at all, right? So if I've got f of x equals x plus 1 all squared, and I wanted to reflect that graph, then it does make a difference if I've got f of minus x. In other words, I'm replacing x with minus x. If I do that, then my graph will look like this. It doesn't flip this time. I do have a separate graph, and you can see that the turning point, say for example, which was minus 1, 1, has now become 1, 0, because every single point here has been flipped over to be negative. So where it used to be here, it is now here. Where it used to be here, it's now here. And where it's the turning point there, it is flipped to be, it was negative 1, and now it's positive 1. So when it's in the middle, like so, doing a horizontal reflection, a reflection about the y-axis, doesn't do anything at all. But if we reflect something a little bit more tricky, then it definitely can move the function as such. We'll talk more about that when we get to reflection examples, though. Just to sum up, if I have a reflection, just refresh this because it's not showing me the right page. Apologies. If I have a reflection f of x going to negative f of x, e.g. y equals negative x squared, the way we write that is the graph has been reflected about the x-axis. If I have f of minus x, so e.g. f of x equals negative x squared, then I would say that's reflected about the y-axis. Okay, so that means that the mirror surface is the y-axis. So it's a horizontal reflection, but it is reflecting around the y-axis. And P.S., just so you've got this clear in your head, negative 1, negative x all squared would be the same as negative 1 times x all squared, which would be the same as negative 1 squared times x squared, which would be the same as x squared. And that's why it's symmetrical. That's the algebraic reasoning why the graph is symmetrical when we don't have any other transformations applied. So I've got a bit of, as you can see there down below, I've got a bit of a careful there. And this is an example of where I've got a translation that's happening first. So f of x equals x squared plus 2 has been reflected about the x-axis. What is the new function? Reflected about the x-axis. So we are talking about this kind of function. It means that the output, the y-coordinate, has been made negative. Now, I've just started off by saying let g of x be the new function. Then, so I'm going to spell this out. You don't normally spell it out as much as this, but I'm going to do it for this video. Then what are we talking about? We're saying that g of x is going to be given by not changing the x-coordinate, but changing the y-coordinate. And f of x is the y-coordinate. So g of x equals negative f of x. But f of x is x squared plus 2. So it's negative x squared plus 2. And that is equal to negative x squared minus 2. If I expand the brackets there, negative times x squared is negative x squared, negative times positive 2 is negative 2. Okay, so you've got to be quite careful about that. If you just think, oh, well, the base function is a square, and therefore I just make it negative x squared plus 2, you would indeed be wrong. And in subsequent videos, we will explain what impact this will have when describing transformation of functions. But we'll leave this video here, and we'll tackle our last transformation in the next one.